So usually I do two activities for points in chapter P. The in-class test covers sections P1, P2, and P6, and that's what this practice test is for. It's to review for the 50-point in-class test over chapter P. And if you can do all the problems on this test, or this practice test, you should be fine for the test. I'll say review for the 50-point proctored test because as I'm writing this, we're in COVID time and we're not having regular classes. The class is online right now. And then sections P3, P4, and P5, there's going to be some sort of assignment, and it varies from semester to semester, but it's going to be some sort of 50-point take-home assignment. And that's not covered on this practice test because this is something you'll be able to do from home. So there's going to be 100 points possible for chapter P. It's just split up between an in-class portion and a take-home portion. The rest of the semester, there's not going to be any take-home assignments. This is the only free 50 points you get. So I'm just going to go through and do all the problems on the practice test. This is a video you really don't have to watch. You might just open up the practice test and start working on it. There are answers at the end of the practice test so you can check yourself. If you get all the answers right, then there's no need to watch the video. But you should do all the problems on the practice test. The test itself is going to be probably a little bit shorter than this. I would guess, the test would have kind of 20-ish problems, 25 max, and this has 35 problems. But I'm just going to start. I'm not going to get into any theory. I'm just going to do the problems how they need to be done. I'm probably going to show more work than you need to do, but I want to see a little bit of work for every problem. I don't want to see you write down just an answer. And when I did the video for section P1, we had problems like this towards the front of the section. And what I did is I rewrote the problem using the commutative property of multiplication and put the terms that can be multiplied next to each other. So the coefficients of 5 and 2 can be multiplied. And when I multiply those, I get 10. And for the variables, I'm going to add the exponents to multiply. The x cubed and x squared, I'll add the exponents and get x to the fifth. The y squared and the implied y to the first, I'll add the exponents and get y cubed. The answer to problem 1 on the practice test is just 10x to the fifth y cubed. In problem 2, the second factor has an implied coefficient of 1 that doesn't really need to be taken into consideration, but if it helps you, I'm going to start off by multiplying the coefficients of 7 and 1. I'm going to multiply the x squared from the first factor and the x squared from the second factor together by adding their exponents. I'm going to multiply the y from the first factor and the y to the fourth from the second factor by adding their exponent, noting that that first y has an exponent implied of 1. And I'm going to multiply the z cubed from the first factor and the z to the fifth from the second factor by just adding their exponents. So to get an answer, I multiply the 7 and 1, or I just keep the 7 if I ignore the 1 part. That doesn't really matter. Add the exponents on the x's, add the exponents on the y's, and add the exponent of 3 and 5 on the z. My answer for number 2 should be 7x to the fourth, y to the fifth, z to the eighth. 3 is the same style of problem. I'm going to multiply the 6 and the 3, the coefficients, the x from the first factor times the x to the fourth from the second factor, the y from the first factor times the y from the second factor. The 6 times 3, the multiplication of the coefficients, gives me 18. When I add the exponents on the x's, I'm adding a 1 and a 4, and I get an x to the fifth. When I add the exponents on the y's, I'm adding a 1 and a 1, and I'm getting a y squared. So the answer for number 3 is going to be 18x to the fifth y squared. When I do number 4, there's an implied 1 in front of the x to the fourth y z term as a coefficient. I'm going to multiply the coefficients of 1 and 5. I'm going to multiply the x to the fourth from the first factor times the x cubed from the second factor by adding their exponents. I'm going to multiply the y from the first factor times the y squared from the second factor by adding their exponents, and the z from the first factor times the z to the fifth from the second factor by adding their exponents. So the coefficient of 5 is going to be gotten from multiplying the 1 and the 5. Adding the exponents on the x's, I get an x to the 7th. Adding the implied exponent of 1 on the y to the exponent of 2, I get a y cubed. And adding the implied exponent of 1 on the z to the exponent of 5, I get a z to the 6th. So for an answer, I should get 5x to the 7th, y cubed z to the 6th. For problem 5, I'm going to reduce the fraction 24 over 6. You can use your calculator to do fraction work if you're not comfortable with it. If I could actually get my calculator to show up. It's hard to get it to show up. Well, I don't know why, but it is. So I can take the fraction, just can't even see it, 24 over 6, and that reduces to 4. It's not even a fraction. So the fraction, I'm not going to get a fraction from the 24 over 6. If I divide 24 divided by 6, I get 4. 6 divided by 6, I get 1. So part of my answer is going to be the number 4. And for the x's, because I'm dividing, I'm going to subtract the exponents. And for an answer, I'm just going to get 4x squared for number 5. For number 6, I'm going to reduce the fraction 12 over 8. I'm going to go 12 divided by 4 is 3, and 8 divided by 4 is 2. Again, if I can get it to show on my calculator, which is really tough, I just can't seem to find a spot to make it show. Just can't get it. So I could do fraction 12 over 8. Has to do with the lighting now, I guess. And 12 over 8 comes out to 3 halves. So the fraction part of this is going to be 3 halves. And for the x, I can either leave the x in the numerator and subtract the exponent of 4 from the numerator and 1 from the denominator, and I can write an answer as 3x cubed over 2. Or, because the numerator doesn't have any any addition or subtraction, I could bump out the x cubed and make the 3 halves more look like a coefficient. Both of these are correct. You can just pick whichever one you care that you feel more comfortable with. For 7, I'm going to divide 9 divided by 3. 9 divided by 3 is 3. 3 divided by 3 is 1. I'm going to subtract the exponents on the x's and do x to the 5 minus 2. I'm going to subtract the exponents of the y's and do y to the 3 minus 1. I don't get any fraction for this because the x and the y's wind up in the numerator because the bigger exponent's in the numerator, and 9 divided by 3 is 3. So for an answer for number 7, I'm going to get 3x cubed times y squared. For 8, I'm going to reduce this fraction by 2. 16 divided by 2 is 8. 6 divided by 2 is 3. I'm going to cancel the x squared, so right now I have 8 over 3 as a fraction. The x squareds cancel, and for the y's, I'm going to subtract the exponents. The exponent in the numerator is shown, the exponent in the denominator is an implied 1. And for an answer, I can either write 8y to the 4th over 3, or because that numerator doesn't have any addition or subtraction between the 8 and the y to the 4th, I can move the y to the 4th off to the right. Both of those are equivalently good answers. In the next group of problems, I have parentheses that don't have any adding or subtracting, and so and an exponent outside the parentheses. To get rid of the parentheses, I'm going to attach the exponent to any number or letter that doesn't have an exponent. I'm going to multiply the exponent by any number or letter that has an exponent. This wouldn't work if there was a plus or a minus inside the parentheses. So for number 9, I'm going to attach the exponent to the 5, and I'm going to multiply the exponents on the x's. 5 squared, I know what it is, and my calculator is not showing up right now, so 5 squared I'm going to write as 25. And x to the 4 times 2 was going to give me x to the 8th. So for number 9, best answer is 25x to the 8th. For number 10, I'm going to attach the exponent of 3 to the 6. I'm going to multiply the exponent of 3 by the 3 that the x already has. 6 cubed is a push. I just can't get this to show. But if I do 6 exponent 3, which I can see but nobody else can see, if I do 6 exponent 3, you get 216. So the number part of this is going to be 216, and the x is going to have an exponent of 9. I should probably write equal and equal. I don't have a habit of not doing that. It's good practice to do that. If you're writing something that's equal to the line above it, this signifies to the reader, I guess, that that's the case. In problem 11, I'm going to attach the exponent of 3 to the 2. I'm going to multiply the exponent of 5 on the x by the 3, and I'm going to attach the exponent of 3 to the y. 2 cubed I can do on my calculator, but it won't show up anyway, so I'll just do it in my head. 2 cubed is 8. For the x, when I multiply the exponents, I get an exponent of 15. For the y, I get a y cubed. Same deal for 12. Attach the exponent to the 5. Multiply the exponent by the x. Attach the exponent to the y. This only works if there isn't addition or subtraction inside the parentheses. 5 squared is 25. When I multiply the exponents for the x, I get an x to the 6, and that y squared just tags along and it's part of my answer. So I should get 25x to the 6 y squared. In problems 13, 14, 15, and 16, if there's a parenthesis that has an exponent outside of it, I need to tend to it first. So in problem 13, I need to deal with the first parentheses, attach the exponent of 5 to the of 3 to the 5, attach the exponent of 3 to the x, multiply the exponent of 2 by the 3 for the y. Don't need to do anything to the second parentheses right now because it doesn't have an exponent outside. 5 cubed is 125. Again, my calculator's just not showing up at all. If I did 5 exponent 3, it's 125. I'm going to leave this in a parentheses, but I probably really don't have to. But getting the exponent out of the first outside of the first parentheses and kind of distributing it through the parentheses, I get 125 x cubed y to the 6th, and then the second parentheses I haven't touched now. Now I'm going to multiply the coefficients. 125 times 7. I'm going to multiply the x's by adding the exponents. I'm going to multiply the y's by adding the exponents. 125 times 7 is 875 apparently. So the number part of my answer is going to be 875. When I add the exponents of 3 and 4 on the x, I get an x to the 7th. And when I add this shown exponent of 6 with the implied exponent of 1 on the y's, I get a y to the 7th. I'm just adding the exponents on the variables. Same deal with 14. I'm going to deal with this right parentheses first because it has an exponent outside. I'm going to ignore the first parentheses. I'm going to attach the exponent of 2 to the x. And I'm going to multiply the exponent of the y, and I'm going to skip a step here just to save time. So that second parenthesis should be x squared y to the 10th. Doesn't have a coefficient. There's an implied 1 that you don't need to write, but you can. Now I'm going to shuffle this up, multiply the coefficients, multiply the x's by adding the exponents, and multiply the y's by adding the exponent. The coefficient part of my answer is going to be 2. For the x's, I'll add the implied exponent of 1 with the shown exponent of 2 and get an exponent of 3. And for the y's, I add up the exponent of 4 and 10 and get 14. So all section P1 so far. In 15, I'm going to ignore the first parentheses because it doesn't have an exponent outside. And in the second parentheses, I'm going to attach the 5 to the x. I'm going to attach the exponent and multiply the exponent of 4 and 5 for the y. Now I'm going to multiply the x's together by adding their exponents, and I'm going to multiply the y's together by adding their exponents. So for a final answer, I add the 2 and the 5 and get a 7 for the exponent on the x. I add the 3 and the 20 and get an exponent of 23 on the y. So my answer should be x to the 7th, y to the 23rd. 16, I need to tend to both parentheses first. First parentheses, I'm going to attach the exponent of 2 to the 3. I'm going to attach the exponent of 2 to the x, and I'm going to multiply the exponents on the y's. Second parentheses, attach the exponent of 4 to the 2, multiply the exponent of 2 and 4 for the x, attach the exponent for the y. 3 squared is 9. So the first parentheses is going to turn into 9x squared and y to the 4th. 2 to the 4th is 16. You could use your calculator if you don't know that. And then you get x to the 8th, y to the 4th. Now I'm going to multiply 9 times 16. It's so frustrating that I can't show you this. Just can't seem to get it. But 9 times 16 is 144. You can't, it's garbage, but it is. 9 times 16 is 144. So the coefficient part of my answer is going to be 144. I'm skipping a step here. I'm going to add the exponents on the x's without rewriting it and get an x to the 10th. And you should probably do the same. I'm going to add the exponents on the y's without rewriting it. And you should probably do that. You don't need to show quite as much steps as I'm showing, but I want to see a little bit of algebra for everything. In the world of 17 through 20, that's the zero exponents. And when we did section P2, there's 3 times where we get automatic ones when we have zero exponents. If we have a parentheses with a zero exponent and there's not a coefficient or an implied coefficient of 1, that's going to be equal to 1. And I did some examples. The quantity 7x to the 0 is equal to 1. The quantity negative 3x to the 0 is equal to 1. Similarly, something like this. Negative 5 to the 0 would also equal 1. If I have a parentheses with a zero exponent and no coefficient to the left of the parentheses, that's going to equal 1. The other instances where we got 1 was we had a positive number, like 5 to the 0 power, or 19 to the 0 power, a positive number without a parentheses with a zero exponent, that's equal to 1. And similarly, this is horribly written or said, but a positive letter, a letter without a negative sign, a single letter with a positive exponent, those are equal to 1. These are the only times that we're going to get 1. Any of the other problems with zero exponents probably aren't going to reduce to 1. So as I look at the 4 problems on this grouping that you can't see, but 17, 18, 19, and 20, 18 is a parentheses with a zero exponent. 20 is a parentheses with a zero exponent. Those both satisfy parentheses with a zero exponent, implied coefficient of 1. Those are automatically equal to 1. 18 is equal to 1. 20 is equal to 1. Negative numbers without a parentheses aren't equal to 1. And when you have a zero power with a coefficient, that's not equal to 1. For problem 17, I really need to think of the negative 1 as a coefficient. I need to think of this as negative 1 times 8 to the 0 power. I need to think of that negative sign as a coefficient. And the 8 to the 0 power is the positive number with the zero exponent. The 8 to the 0 power is equal to positive 1. But I have to multiply it by the coefficient because this is kind of an orders of operations problem. I do the exponent before the multiplication. And then negative 1 times 1 is negative 1 because positive times negative is a negative. The answer to 17 is negative 1. Similarly, number 19, I need to think of this as 16 separated times y to the 0. The 16 is a coefficient. It doesn't turn into 1. The positive letter to the zero exponent turns into 1. And in problem 19, this is really 16 times 1. the y to the 0 power is equal to 1, and then 16 times 1 is 16. The answer to number 19 should be 16. All right, we keep plodding along, and now we're pretty soon going to get to the grungy part. We get to the negative exponent part and the division part. So 21 through 28 are the negative exponent parts of section P.2. I'm going to start using the rule that x to the negative n, if I have a fraction, I can make the fraction have a positive exponent. If I make a fraction with a 1 in the numerator and the exponent in the denominator. In addition, I'm going to use the rule that if I have a fraction with a negative exponent, that I can make that negative exponent positive if I flip the fraction. For some of these problems, I'm going to use the shortcut to avoid negative exponents, and I'll get to that as I get to it. In problem 21, I really need to think of this as 4 times x to the negative 3 power. Because there isn't a parenthesis, the exponent of negative 3 only impacts the x and not the 4. The x to the negative 3, I can use the rule that any negative exponent can be made positive if you create a fraction with a 1 in the numerator. The 4, I'm going to write it as a fraction. And now I'll be able to simplify and get my answer written with a positive exponent. Here I've changed this non-fraction problem into the multiplication of two fractions. And when you multiply fractions, you multiply across the numerator and across the denominator. So to simplify this, I'm going to get 4 times 1 in the numerator, which is 4, because anything times 1 is itself. And 1 times x cubed is x cubed. I get that in the denominator. Again, anything times itself is itself. The next 1, 2, 3, 4 problems, I'm going to avoid negative exponents. If you have a problem that's a fraction and there's a letter in the numerator and a letter in the denominator, I generally don't like to introduce negative exponents if I don't have to. And I did this trick quite a few times in section P2, but not every time. Some of the problems I did 2 ways. I'm going to show you the trick again just in case you forgot it. To start problem 22, I'm going to reduce this fraction. I'm going to go 12 divided by 4. 12 divided by 4 is 3. I'm going to go 20 divided by 4. 20 divided by 4 is 5. When we worked in section P2, eventually I started doing this trick over and over. If I have a fraction with a letter in the numerator and a letter in the denominator, my answer, the letter's going to wind up where the bigger exponent is. And if I look at the exponent of 2 for the x is the bigger of the 2 exponents in the denominator. So my x is going to wind up in the denominator, and I have to subtract big exponent minus small exponent to get my answer. The exponent for my answer on the x is going to be x to the first, and it's going to be in the denominator. So this is a negative exponent avoidance strategy that's important to, probably good to use. I could have done this problem differently, but it'd been a lot harder to follow, and it's not the way most mathematicians would do this. So for 23, I'm going to start off dividing 12 divided by 2 and getting 6, 2 divided by 2 and getting 1. I'm probably not going to need to write the 1 in the denominator, so I'm not going to worry about it. Now I look at the x's and ask myself where the x is going to wind up. The x is going to wind up where the bigger exponent is. The x in the numerator has an exponent of 1. The x in the denominator has an exponent of 4. So I'm going to take the x. I know it winds up in the denominator because the bigger exponent is there. I'm going to do big exponent minus small exponent. Similarly, if I look at the y, the exponent in the numerator is 3. The exponent in the denominator is 7. The y is going to wind up in the denominator because the bigger exponent is there. I'm going to do big exponent minus small exponent, kind of cheating this rule a little bit, shortcutting this rule, but this strategy will work every time. So in the numerator, my answer is going to have a 6. In the denominator, I get an x cubed and a y to the 4th. If the x or the y was in the numerator, I could drag it off to the right, and make it not part of the fraction, but you don't usually do, if the letters are in the denominator, we don't drag them off to the right, because if I drag them off to the right, they need to be in the denominator of a fraction that has a 1 in it. For 24, the fraction 12 over 8, I'm going to divide by 4. I'm going to go 12 divided by 4 is 3. 8 divided by 4 is 2. I'd show you on my calculator, but my calculator can't show that right now. The x's are identical. They're going to cancel. The y is going to wind up in the numerator because the y has an exponent of 6 in the numerator, 5 in the denominator. I always decide where the letter's going to wind up. The y is going to wind up in the numerator because the bigger letter's there. I subtract big exponent 6 minus small exponent 5, and I'm going to get 3y to the first over 2. This is a time where I could drag this around and make it look a little bit different. And I'll go ahead and do that. It's not necessary to do it, but it's not a bad idea. It's kind of, a nice looking answer. And the alternative answer, if you get straight multiplication in the numerator of a fraction, any letter or variable, I could call it, can be drug off to the right. Both of those are acceptable answers. For problem 25, I'm using this shortcut. If I have a fraction with a negative exponent, I can invert that fraction, find its reciprocal, and make the exponent outside, positive. Now I'm going to go to the attach and multiply. I have a fraction, or inside a parentheses there isn't any addition or subtraction, and there's an exponent outside the parentheses. I can multiply that exponent by any number or letter that has an exponent, and attach that exponent to any number or letter that has an exponent. So in the numerator of my answer, I can get x to the 16th, x to the 8th, that's an 8, and in the denominator, 4 squared is 16. If I wanted to, I could have thought of this as 1x to the 8th over 16, and if I thought of it like that, I have a ability to rewrite the problem so that the x isn't buried in the numerator, but that's not necessary. These are both correct. They're equal to each other. For 26, I'm going to invert the fraction and make this 2 over 3 to the positive third power. I'm going to attach the exponent to the 2 and get 2 cubed. I'm going to attach the exponent to the 3 and get 3 cubed. Calculator is worthless right now, so I'm just going to do these in my head. 2 cubed is 8, 3 cubed is 27. If you don't have them memorized, use your calculator. 27 and 28 are here just to illustrate the difference and simplifying with dividing depending where the bigger exponent is. In 27, the bigger exponent 5 is in the denominator. When I simplify this, the x has to wind up in the denominator. I take big exponent minus small exponent, leave the letter where the bigger exponent is. In problem 27, there's nothing left. It's kind of naked. I can't write a fraction without a numerator, so I need to leave a 1 behind. For an answer, I can write 1 over x to the 7th. The alternate way to do this, which is maybe the more proper way, I could have thought of this just using the rule that says if I'm dividing, I subtract the exponents. So this could be x to the 2 minus 5 power, which is x to the negative 3 power. I wrote a wrong number here. This 5 minus 2 should have been 3. The answer should be 1 over x to the 3 because 5 minus 2 is 3. I don't know why I added them. Getting back to this, the proper way to do this is to subtract the exponent. You'd get x to the negative 3 power. Then I could use the rule that says if I have a negative exponent, I can make it positive by creating a fraction with a 1 in the numerator. 28 is no worries. The bigger exponent's in the numerator. I don't have to do any sort of trickery. I just use the rule that says if I'm dividing, I can subtract the exponents. My answer is not going to be a fraction because the bigger exponent's in the numerator. You only get a fraction if the bigger exponent's in the denominator. I have 7 problems left. They're all from section P6. I think I'm going to stop this and make a part 2.